Couple quick announcements. So, first reminder, Canvas Quiz 3 opens this Saturday. As we walk up to the next midterm, you're going to have quizzes next couple of weeks. Each one of them is going to kind of keep tabs with what we've been going through, the lecture material. Good practice to kind of continue through. Midterm regrades, as we mentioned before, those should be due. Get any requests back by this Friday. Also remember, midterm 2, I should have adjusted all the CFA times. I've cleared that part back up. If you have any other questions or problems, please do let me know from that point. And other notice that the final exam is now set. So last class, we talked about our derivatives of carboxylic acids. This is now where we're taking amides and reformatting them back to our carboxylic acid. We talked about isocyanates. These are kind of the weird cousin with like a carbon in the middle that is an sp carbon, these linear kind of structures. And just start to introduce organometallic reactions. These are additions of strong nucleophiles like Grignards and alkylithiums into molecules like esters. So how would you do this? What's your synthetic transformation to take that starting material to that product? Okay. So this is a synthesis question. You're asked to take a starting material to a product, so you're asking for conditions, right? First thing you should start to do when you look through something like this is what is different, what's added, what's subtracted, what's changed. So give me some highlights. What are you guys seeing? Give me some clues of what's been added to this molecule, for example. What's new? Yeah. Well, okay, Grignard, but more specifically, what's new about here? Carbons, hydrogens, what's the new fragment that's going on, right? Yeah, you've got this chunk and this chunk, which probably means you formed that bond and that bond. The rest of the molecule, this piece here, is still that part here, where again, what you're doing is you're targeting in pieces of this to say where the business end of it was. That's the carbon mapping that probably matters. So you're focusing in on that blue carbon. That's probably going to act as your electrophile. And the two other fragments, the ethyl fragments, are being added as nucleophiles. This sounds a lot like a Grignard or an alkylithium, where these guys probably came in as, let's say, MgBr ethyl, right? And you're going to do two equivalents of it. All right, so can I go straight at this? This is back to the, more power, more force. If I just mix these two together, Grignard and this carboxylic acid, you just do an acid-base reaction. So the direct route is not going to work. What do you have to do to your starting material to get it ready for that step? This is your closing step for sure. Yeah? SOCl2 into an acyl chloride. Yeah, you could convert this into something like SOCl2. That gives you your acid chloride. Now you're good to go, right? This is now electrophilic. You've removed the acidic proton. Isolating that gives you something that's going to do two additions, right? The first addition gives you your ketone. Second addition gives you tertiary alcohol. What else? If you didn't want to go this, what's another way that you could possibly do it? Yep. Yeah, you could go by a way where if I took protons and let's say, I don't know, methanol, I could make my methyl ester. So those are two different ways that both will work, right? What most important is I have to replace that carboxylic acid. It has to be something like an ester or an acid chloride. Both work. If I have to look at the two reactively, ester versus acid chloride, which one is more electrophilic? Acid chloride. So if you are a wild man, looking at you, this is what you're going to go and do. If you are a lot more safe and reasonable, ester. Reason why in this case, now again, give me an example. Why might this matter? If I had to talk about how fast that second step is, adding the carbon nucleophile, Which one do you expect to be quicker, red or blue? Which is a more reactive electrophile between the two? It's going to be your acid chloride. So that second step is going to be way more reactive and probably a quicker reaction with your acid chloride. In this case, the Grignard is so reactive, both will work. One just may take you longer. Right? This is not a case where both of those two answers will work out, but if the nucleophile was not nearly as good, you might have to use the acid chloride. If the nucleophile was something a little bit weaker, you might need the extra power in your electrophile. In this case, the Grignard is a phenomenal nucleophile. Both will be accessible. But more importantly, also, you're getting this double addition. So today, we're going to introduce the last part of our acyl substitution and acyl transformations. This is where we're going to look at the last part of the electrophilic addition and electrophilic reagents. And we're going to start talking about carboxylic acid derivatives as they're reduced. This is where we're reducing lithal and dibal. We mentioned this part before. We're going to look at the mechanisms and stuff today. And then finally over to what I call our Gabriel amine syntheses. So if I looked at these two, and I just was going to do a spot check, this is just a reminder example of what we talked about last time. Excess ethyl magnesium bromide with the first molecule versus magnesium bromide, the phenylmagnesium bromide, second molecule. What are your two products in these cases? What are you generating? So in the first one, that's going to be my nucleophile. If we have excess, we have as much as we need to add to this material. If I'm doing the decomposition of this, this is my nucleophilic species. That means the electrophile we're focusing on is going to be my carbonyl. This is my ester. Remember, when you add to the ester, that's the bond I'm going to be cleaving. It's between the carbonyl and the oxygen. This piece right here makes up my leaving group for that nucleophilic addition. So I'm actually going to fracture that ester. Now, because it's cyclic, remember this is a, do you remember the name of this? Cyclic esters have a special name. It's not lactams, it's a lactone, but it's just an ester, right? So if I'm breaking this part into pieces, my nucleophile is going to be my ethyl species. My electrophile is over here. I'm going to have 1, 2, 3, and 4 pieces to it, so I'm going to draw that part out like this. That's going to be my carbon 1, 2, 3, oxygen, OH is number 4. When we're all done, that core piece of it's still going to be retained, right? We've broken off the alcohol, it just happens to be attached by way of your carbon chain into the center. Carbon 1 here, I'm leaving it just agnostic as a dot right now. That's the center readdition is happening. If we add, let's say, a Grignard to this one, it will add twice. So we're going to have ethyl and ethyl attached to that center. The reason it's adding twice is because the ketone intermediate we're generating is more reactive, so after workup, that will also be an alcohol. So this is kind of the decomposition for how you might go through this part. Identify your nucleophile, electrophile, find your pattern, where's the bond breaking going to happen, what are you adding to what, but in the end, because it's cyclic, it just looks a little bit more complicated than the previous examples we've had. It still has this tertiary alcohol that we formed off. The alcohol leaving group that we're using, whatever we ejected, is just this one on that pendant side. Now we introduced this other one in our second step, or very end of last class. This is where, again, my nucleophile is going to be here. My electrophile over here, where that's the carbon center we're going to be adding to. The oxidation state of this nitrile is similar to a carboxylic acid. It's like the ester or like an acid chloride. What's different about a Grignard addition to a nitrile? What's your final product in that case? 2 additions or 1? Yeah. Just 1 addition. What's happening here is I will add these pieces together, and I went over it in the Try It Later video in class, posted online now. That means this is my fragment that I'm going to be, my electrophilic fragment is this isopropyl, whoops. Oh, ooh, what happened there? Boop. Hold on one sec. Bloop. 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 Oh. Wrong power. There we go. Ha ha ha. So, this is my isopropyl fragment. That is the carbon that I'm adding as my the center where my electrophilicity is adding to it. I'm adding my Grignard, so my phenyl is being added to it here. And the functional group that's left over, since it's a single addition after workup, will be this ketone. And again, this is what's happening here is the addition product here, adding to that nitrile, creates an iminium anion intermediate, which is stable in the reaction conditions. Only until workup does it get converted back to this ketone. So what's happening in the second case is we're still doing a nucleophilic addition, but because we now have this carbon triple bonded nitrogen, the intermediate we generate is no longer a ketone, it's a masked ketone. It's a protected ketone that doesn't actually get exposed until this workup step that produces your final component. So that's where you have this ability to select one versus the other. The thing that I'm trying to highlight here is there's two kinds of reactions we can take advantage of. There are reactions which produce intermediates that will continue to react under the reaction conditions, like we have in the first case. And there are reactions where the intermediate persists or otherwise holds on to the reaction conditions. It is immune to further reactivity until we do workup. So these are these two balances, and this is what we can get selectivity based on. That's what we're going to use for some of our reductions. So reducing agents you've seen before, lithal, lithium aluminum hydride. This is the most powerful reducing agent we can introduce you to, you guys. It levels everything. There's not a carbonyl type containing group that it will not destroy. Sodium borohydride is the slightly more gentle version of the two. It hits aldehydes, it hits ketones, it hits imines, but it won't touch carboxylic acids. It won't touch esters very easily. It's not nearly powerful enough for that. Lithal is your big dog. Diabal is the one that we're introducing now as new. It's still an aluminum hydride type reagent, but now notice it has only a single aluminum hydride. It has a stoichiometric single hydride equivalent. Lithal, one molecule of lithal has 4 H minuses baked into it, but also reactively, lithal is far more powerful than diabal. And we're going to talk about the mechanistic distance between the two. Really what we're going to be able to do is use this kind of part to focus on selectivity. So we mentioned this briefly before. Lithal is ridiculously reactive, far more than sodium borohydride. It is powerful enough to just look at what we talked last time. You know, can you do a reaction of acid chlorides? And over and over and over again, I've been saying, nah, that's just an acid base. Nah, that's an acid base. If you take an amine to this, nothing happens. You take a Grignard to this, nothing happens. Lithal does not care. If you take lithal and your acid chloride, it's like, cool story, bro, we're still ripping you apart. You will get down to the primary alcohol, where what you're doing here is you're actually doing 2 equivalents of an addition of those hydrides into that part. This also means, from a perspective of deuteration, if this was lithium aluminum deuteride, you would make the deuterium here and here, because this is really what you're doing is you're adding H minus to that center. It's a source of nucleophilic, either deuteride or nucleophilic hydride being added to this carbonyl. And it's the full reduction. Remember, in the oxidation states we were talking before, this would sort of be level 3. It's a carbon attached to 3 carbon oxygen or carbon heteroatom bonds. Aldehyde ketone, that's like number 2. You only have a double bond. Alcohol, level 1. You've taken it all the way down from 3 to 2 to 1 when we went through a system like this. And this is kind of like what we talked about with the Grignards. Lithium aluminum hydride, there is no stopping. It still will happen progressively. You're not jumping 2 oxidation states in one step. It's a single sequential step where you start from the highest oxidation state, acid chloride and hydride or ester, and all of them are being reduced down 2 oxidation states to your final component. So what we're saying is it doesn't really matter on that entire spectrum of compounds that we've looked at, you're completely knocking it all the way down. Yeah?
In the earlier slide, if we use deuterium, would we also exchange the 1 hydrogen?
This one right here? What do you guys think? Good question. Will you exchange, let's say if my conditions were lithium, aluminum, deuteride, where my workup was H3O plus water. Who says yes, that OH becomes an OD? No. Why not? What's that? That OH is like H plus. Lithium aluminum deuteride is H minus. So it's the nucleophilic source of deuterium, not the protic. If you wanted to exchange this one over here, that has to be deuterium. Make sense? Okay. So lithium aluminum hydride is the great reset. Who watches Ryan Trahan? Oh, come on. Somebody else has to. He's such a cute boy. This is the great reset. We can take every one of these compounds and we can completely level it back to its primary alcohol. We're taking the end of a chain of some carbon system, and we're completely removing any functionality that used to be there from this higher oxidation state. It doesn't matter what we start off with. So the good news is it's reliable. Bad news is you have no control. You cannot stop in between. We're going to go all the way through to these parts. How it happens. This is the mechanism part. Now, the interesting thing with these two, dibal and lithal, are two new mechanisms we're going to go through. And this is where I want you guys to remember back. Remember the kind of the three buckets of nucleophilic substitutions we talked through? There was, what were they? We had three general categories of reactions. So give me one. So strongly acidic, strongly basic, and then mild, right? Let's look at those first two, strongly acidic and strongly basic. What was the key thing for a strongly basic system? Your nucleophile was what? Strong nucleophile, it's like O minus, N minus, right? It's a negatively charged nucleophile. And then the strongly acidic one, what was the key thing there? What was the really key thing that was different about that mechanism for strongly acidic? What did you do to the carbonyl? You activated it, right? The acid's job was to make the carbonyl more electrophilic. The strongly basic conditions, the nucleophile is already negatively charged and can already attack. Those two things are going to be repeated in these mechanisms. So look at this condition here. If I have an electrophile, that guy, my nucleophile here, what would you rank this as? Strongly basic, strongly acidic? If you had to choose, what does this look most like? Strongly basic. You have a negatively charged nucleophile. This is your nucleophilic species, and it's negatively charged. This is a source of H minus as hydride minus, right? The aluminum hydride is a negatively charged species. So your opener is going to be very similar. This is nucleophilic addition directly to my electrophile. I don't yet need to activate my carbonyl. The carbonyl here is going to basically be, we're laying waste to the carbonyl because we have a negatively charged nucleophile already present in my system. Okay, so I do this addition, I will get a tetrahedral intermediate O minus, I've got OR prime, and I've now added one equivalent of hydride to this one. What happened to the aluminum, though? Let's keep track of that point. As I did this addition, left over is now aluminum, HHH. The negative charge used to be on the aluminum hydride. We've transferred one H minus. That means I'm left back with a neutral aluminum. It's a tetravalent aluminum to start off with. You now have a trivalent aluminum to give in. Now again, I don't have a periodic table here, but what do you guys know about aluminum in terms of which row it's in, right? It's under boron. Does it have a lone pair? No, it actually has this guy right here. It's neutral like this, right? That's the right formal charge, but it actually has a vacant orbital here. There's no lone pair. It's not nitrogen, but it's a vacant orbital right there. Do you guys remember what this kind of thing is called? A neutral molecule, vacant orbital. It's an electron acceptor. Lewis. Acid or base? Acid. Lewis acid. Lewis acid. This is not Bronsted acid, H+. It's an electron acceptor. Lewis acid, it happens to be neutral, but it's still an electron acceptor. This is a Lewis acidic material. So that's going to come into, we're going to use that feature of it later, but the main thing I want to focus on here is these kinds of reagents, these aluminum, these boron reagents, what they do is they actually move between two different coordination spheres. The tetravalent one will be negatively charged. That's based on the formal charge of your system, right? The valence orbital says if I put four things around it, it's going to be negative. The neutral system is actually, well, I've got this open, I've got a vacant site. I'm actually looking back for those electrons. Effectively, aluminum and boron are just never happy. You give them all this, the saturated environment, oh, I'm negative, I want to get rid of this thing. You get rid of it, oh, now I want it back, come on, man. So we can use that for reactivity. So now we have a system like this. We've done that first addition. If you look at the complex we just formed, this is balanced off by lithium, right? But look at this compound. If this was a strong nucleophilic addition, strong nucleophile addition makes a tetrahedral intermediate that I'm going to bring down this charge, and I'm going to eject my group, right? This is your collapsed or your tetrahedral intermediate that you've used before. That's going to give you your what? What function group did I just make? I made an aldehyde. So now that you've done this, I kicked out my hydroxide. Why is that possible? Well, I had a hydroxide. I'm making a hydroxide. Energetically, we're balanced. I made an aldehyde from this one. I've got a single hydrogen and an R. Aldehydes are more reactive than your starting material, your esters. And now I also have this Lewis acid kicking around. What that just means is if I have a nucleophilic species like this and a Lewis acidic species, these guys can coordinate. I've got a vacancy of electrons as this trivalent aluminum. I can recoordinate my aluminum back on to make this OR complex. What that's going to do is I'm going to make aluminum H, 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 OR prime, right? What about the charge? Negative. If I coordinate that species back on, now I'm negatively charged. Now, go back to the very beginning. What was the rule we said about these aluminum complexes? If they are negative, they're what kind of nucleophile? Good nucleophile, strong nucleophile, or weak nucleophile? So we just took the aluminum. It dumped that hydrogen. For a second, it's like, man, I'm so happy not to be negative. I better go find a negative charge. And now it's negative again. Now that it's negative again, it's a good nucleophile again. And I happen to have a really, really electrophilic carbonyl here. I've set myself up for doing one more reduction because I've recharged my aluminum. It's now aluminum hydride again. Now that it's aluminum hydride, it's going to go through and attack. So that second addition gets me my R. We're going to go back to another tetrahedral intermediate. We've transferred that second hydrogen. So here's the first one. Here's the second one. And the final aluminum is just, it did that final transfer. You're going to have your RO prime balanced to aluminum, and it's going to be trivalent again. So it's the switching behavior. You're starting off with this tetravalent negative aluminum, pass over hydrogen, neutral, Lewis acidic, grab back my negative charge. Oh, I'm negative charge again, transfer the next hydrogen, on and on. And what we've done here is now we have a complex that now it will sit there and there's nothing else we can do. We've done our full reduction. On workup, when I work this up, I'm going to get a proton added back over here. That gives me my alcohol. I'm not going to go through the mechanism in detail in class here, but what do you think happens to that once we give it water and protons? Remember, what is this hydrogen on aluminum? Is it H plus or H minus? H minus. If you give it H plus, what do you make? H minus with H plus gives you hydrogen gas. This guy's job, once you give it water and protons, that simply becomes, here, let's go over here. That species when we give it water and protons, we're going to eventually get, after everything's said and done, your aluminum will now be bonded usually to 3 or 4 hydroxides that came from the water. That's negatively charged. You're going to make hydrogen gas. That's where these end up going out of the system as H2. And eventually, you're going to be able to exchange that off as just RO alcohol. It will just be protonated back. Again, I'll go through the full mechanism of how this happens for anybody interested in the class after. It's not necessary. You don't need to. The thing that you have to focus on is the way that this works with lithal. One, lithal is already a very good nucleophile. It can do this addition where it's adding to the carbonyl directly. That addition to the carbonyl creates a tetrahedral intermediate, which is going to eject, close, and kick off that OR group. You now have a Lewis acidic species. This is your trivalent aluminum that's going to coordinate together to give you your new aluminate complex, H minus again. That goes through a second cycle where we've not only exposed my aldehyde, it's present in the course of the reaction. I didn't have to work it up. It spontaneously forms. And since that aldehyde is being formed and we have another hydride equivalent, we go through a second addition to give us our final compound. What we're just showing here is that probably it can sit there where, once again, this is a Lewis acid-base reaction. They can coordinate together. But on workup, you're getting back your tertiary alcohol the alcohol fragment from the other part of the ester, and then eventually this is all the aluminum salt where those hydrogens, any unreacted hydrides go out as hydrogen gas. But that's all in that final sort of workup exchange. So there's kind of two new things here. This is still just strong nucleophile addition to a carbonyl. Why this is possible is that aluminum goes through these two different states. H-, which is a source of hydride to attack into a system, and this more neutral aluminum that acts as a Lewis acid. It's doing this job where it's coordinating out to the system and helping to remove. The one big thing here is aluminum and oxygen. That is a match made in heaven. Does anybody know things like silica? Right? Silica is silicon dioxide or silicon tetraoxide, right? This is silicon that's bonded to oxygen. Aluminum and aluminum oxide like this, that makes up bauxite. That makes up a very, very stable species. So once you can get down to a compound like this, energetically, we've gone super, super, super far downhill to make a very stable complex. So we're going to go through this, what the products of something like this, and I'll walk through the mechanism for this in the video after. This is a reduction of this compound where we're going to keep track of where centers are breaking out. Next, again, this is what would happen to esters. You get the primary alcohol. Acid chlorides, primary alcohol. Carboxylic acids, primary alcohol. The only thing that's different is amides. If you do a reduction with lithal and an amide, now you're ending with the primary amine, not the primary alcohol. In the end, if you follow through what's actually happening with all the species, these oxygens are still going to be eventually associated with the aluminum. You're still adding 2 hydrogens to the center. The difference is the bond that actually fragments here, we actually retain the carbon-nitrogen bond. We throw away the carbon-oxygen bond. There's 2 reasons for this. One is, remember, the amide that you have here, because of tautomeric equilibria, the other way to think about this, this amide is also looking at it like OH, double bond, nitrogen, right? So in the same way as what we did before, where we're targeting that sort of OR, we're using the same kind of a mechanism where that single bond part is what's being ejected from the system. We can access structures like this, so it follows the same sort of mechanism as we go through. And again, I'll go through the longhand mechanism of this after if you're interested. But the most important part is how we do that this final removal after we've got this choice of which bond we're going to fragment. Carbon-nitrogen versus carbon-oxygen. Think about this from the perspective of those 2 pKa's. If I took a pK of something like an alcohol, ROH, its anion is the alkoxide. What's the pK of an alcohol? ROH, pK is 16. If the amide was being kicked off, instead of O- being kicked off, it's still going to be anionic. You'd be kicking this off as N-. What's the pK of ammonia? NH3 neutral. pK is way higher. Basically, there's going to be a step in the intermediate. Reason that nitrogen gets retained is you're going to have an intermediate that's going to have to choose. Do I kick off O- or do I kick off N-? O- is going to win. N- is going to lose. That's why this bond, that carbon-nitrogen, is retained in this point. The mechanism will look very similar to what we just went through. You're just going to be substituting, instead of oxygen, one of them is going to be a nitrogen in there. And you should be able to rationalize there's an intermediate where it's going to have to make a choice. Oxygen is going to be the one that loses. Same thing here. This is that same kind of hydrolysis where we're doing 2 additions and we're ending up with 2 hydrogens added to this point. It's a little easier because we're not trying to extrude oxygen from this system as we go through it. So that's how you introduce these primary centers. So if you had to look at this from this point, remember, this is where go back and forth between these two slides. Notice what's happening in this part here. If I'm mapping this out, the carbon that used to contain my carbonyl is right here. We've retained the carbon-nitrogen bond. We've extruded or destroyed the carbon-oxygen bonds, both of them, and replaced them with hydrogens. So that's the mapping that we kind of go through this point. So if we had to do this backwards, I'm showing you the products here. In the first case, if this was a reduction of an amide, what would that amide look like? If I had to work backwards, so I'm going to number this off. 1, 2, 3, 4. Where was the carbonyl? This is your product. I've given you these numbers where carbons 1, 2, 3, 4. Where was the carbonyl to start off with? Carbon number 1. So if I'm working backwards here and said it had to come from an amide, first thing you're going to do is redraw the structure. the carbonyl was right here because if you look in your product, that's the center where you've added these two other hydrogens to. It's adjacent to the nitrogen. And if you look at 2 points, 4 does not make sense. You've already got 2 methyls there. The only center that you could have done a reduction to get you this product can't be carbon 4, 2 methyls, can't be carbons 2 and 3. Those are too far away from my center. It's got to be carbon 1, used to be a carbonyl, and we've now extruded it out. This is why this reaction can end up looking a little bit weird, because the molecule looks fundamentally different now. You start off with this amide, we've done these hydrolysis steps you've been practicing in. Now we've got a way of reformatting it almost like Clemenson, almost like Wolff-Kishner, where we're removing that functional group and reforming it as a much lower oxidation state. What about the second one? Here you've got actually a marker. You've got deuteriums, and we came in here. So once again, 1, 2, 3, 4, 5 has to be at carbon 1. So we're going to have a 6-membered ring. This is still going to be an NH. I'm going to have a carbonyl here at carbon 1. What about carbon 4? What has to go at carbon 4? Methyl group. Does the geometry of that methyl group change in the course of this reaction? No, it's coming along for the ride. This is going to be identical to what we had here. That's a remote functional group that has no change in stereochemistry. It's coming along. So this is the other way, is if we had a product, we could know where the carbonyl was, either by deuteride addition. Deuterium gets, or the deuteride gets incorporated where the carbonyl was. So those 2 additions come from this lithium aluminum deuteride. The other one is a molecule like this where you have functional group blocking. There's only one center that has that CH2 for these kind of additions. Does that make sense? Okay, cool. Now, that's the Great Reset. That's how you knock down these molecules. Dibal is your selectivity. This is your surgical way of doing it. Dibal can actually take an ester down to the aldehyde and stop. So we don't go through 2 reductions. We only end up with a single. Dibal, same thing here. At higher temperature, though, will end up with 2. So the key difference here is dibal, very low, very cryogenic conditions. This is surgical. I could do 1 addition. In the second conditions, if I take the exact same conditions but I run them at too high of a temperature, if I let the reaction warm up, you lose your selectivity. So there's a key thing going on here where because of temperature, I'm controlling which intermediates are possible, I'm controlling which intermediates are stable, and as long as I can stabilize the intermediate under these cold conditions, I can do this addition here. The other thing that's really helpful here is since dibal, it's no longer this tetrahydride material. It has a single hydride. It gives me a lot more control. 2 equivalents of dibal will be necessary for that second addition. Here, all I'm saying is that if this happens to be warm temperature, that will be your more stable compound, but you'll probably end up with a 50-50 mixture of these 2 because you're going to have to require or eat 2 equivalents of dibal to make 2 reduction events. So it's not that this is stoichiometry that's allowing to hold onto your aldehyde. The problem is your ester is way less electrophilic than your aldehyde. If you allow the system to warm up, the ester will still turn to the aldehyde, and then it will be exposed. It will be present in the reaction system that it can still be hit by that second addition. All we're trying to emphasize is dibal is not magic. It will hit esters. It will hit ketones. It will hit esters. It will hit ketones. It will hit aldehydes. Esters just give us a small window of opportunity where we can add this selectivity to stop at aldehydes if we want. This reaction here is why we typically use dibal, is because we're trying to enforce selectivity. So, yeah, again, coming from the prairies, this is basically walking outside on a very, very icy day with polished sandals. You got to be really careful to do this part right. How it happens is, again, you're mixing these 2 species together. And back to those 2 general mechanisms we talked about. Strong base, strong acid. Does this look like strong base anymore? Do you have a strong nucleophile? No. But what do we say about aluminum that's trivalent? You have an open site. This is a Lewis acid. This is equivalent to an acidic or strong acid type mechanism. Since I have this open valent site here, first step I'm going to do is coordinate. It becomes an electron acceptor, just like protonating the carbonyl with an H+. we're protonating the aluminum, or protonating the carbonyl with my Lewis acid. So this is our openers. What we're doing is we're coordinating this part together. We're taking a neutral aluminum species and we're activating it. At the same time, we're activating our carbonyl. So that addition now gives us our OR, OR prime. We're now bonded to aluminum. We've got our two bulky alkyl groups. Let's go another color. There's our hydrogen. What about charge? Aluminum, what's the charge on aluminum based on this coordination environment? It's going to be negative, right? What else? Do I have any other charge? I start with two neutral things. I can't just create negative. Positive on oxygen. You've protonated that center, right? So you've activated this. So now you've done two things here. One, I've activated my carbonyl. It is now more electrophilic. I've now made this much easier to accept a charge. Two, I have activated my aluminum. It's now anionic. Now it's a nucleophile. Now it's hydride equivalent, right? So now I can take this hydride and use it as a nucleophile. Now I'm drawing it in the same molecule. This is a convention that makes it easy for everybody. Actually, it's probably one of these molecules finds another molecule, and it's one hydrogen from one to the other. The only reason I'm saying that is if you actually build this model kit, this is hard, right? If you actually tried to line this thing up where that oxygen, aluminum, hydrogen did this inside attack, it's a pretty tight little system, right? Because you've got 1, 2, 3, 4 bonds here. Now possible, because aluminum, what's the size of aluminum? It's third row, it's pretty big. So yes, it's a 4-membered ring, a little bit flexible. Again, I want to draw this as a convention where it's a hydride from the aluminum negative is attacking a carbonyl. But if you imagine this in terms of is this allowed, it's much more likely that one of these molecules finds another molecule. One's acting as nucleophile, one's acting as electrophile. But still, this is what you get. And then up to here. So that's done two things. You've done your hydride addition, you've satisfied your charge, and you've now made a tetrahedral intermediate. Once we do this, we're going to have our R group, O. You have your OR, whoops, color, OR prime. We have our aluminum. It's no longer a hydride. We've transferred that over here. And we've got our two groups attached. What about charge? Are we happy? It's good. Everybody's stable. Nice thing about this complex is if temp is low, minus 78 degrees, absolutely nothing happens. Because remember, normally, if we're doing the next step, if this is a normal acyl substitution, how do I collapse my intermediate? If you've made this tetrahedral intermediate, normally what's the next step that happens? O minus comes back down, kicks off OR prime, right? If this is an oxygen to aluminum bond, oxygen is no longer negatively charged. It's actually kind of balanced. It's using the aluminum as a crutch right now. The aluminum is not going to be charged. There's nothing else it can transfer, nothing else it can do. It's acting as a protecting group, effectively. So instead of having this as an alkoxide, there's that aluminum-oxygen bond. So having this key bond right here, it's fragile. As long as you keep the temperature down, it's going to pause right here. It freezes in place, and that's all you're going to have. Nothing else happens, which means even if I had more dibal in the system, right? If I've got this floating around in the system here, that molecule looks at this molecule, and I can't do anything. That's not an aldehyde. If you had to look at this, like focus in. Here, whoop. What's that functional group? If you had to give it a name, that is a badly drawn acetal, right? R carbon, O to what I have here is I have carbon, carbon center, hydrogen, two OR groups where one's a carbon, one's an aluminum. That's an acetal. It's protected. It's barely protected because it's an aluminum oxygen bond, but it's a protected group. Acetals are not going to be reduced by lithal, by anything else. This is basically what you just did, is you created a protecting group in the course of the reaction. So it's going to be stable. It will sit here. Yes, if you warm it up, if you warm up this reaction, you can fracture this bond. That can expose that O-, then it can collapse back in, and it basically pops out the acetal. The acetal will collapse back to the aldehyde. But this key intermediate here, it will freeze in place until the reaction sort of works forward. So what we can do to complete this mechanism, oops. I'll just redraw it. Bloop, bloop. We've got our oxygen, aluminum. You've got your two alkyl groups. You've got your OR prime, and you have your H. If in step 2 we now add acid and water, now you've given the aluminum something else to hold on to. You've given it a proton that can now fragment that oxygen to aluminum bond. So in doing that, we're going to get our R, O, H, O, R prime, and H. That's the immediate thing that we form. And eventually, the dibal, again, is going to form into something like aluminum. Your two alkyl groups are still attached. And then OH, OH minus. It's the salt. This is kind of the junk from the reaction that's going out with the actual, whatever your product source was. If you have your H3O+, it's just going to balance that part out. So that's the fate of the aluminum. It's going to be some type of a complex over here. But if you notice this, that is what? It's not an acetal anymore. Now it's a hemiacetal. Hemiacetals, under mildly acidic conditions, can turn into aldehydes. So if we continue, this part here is going to collapse, right? And that's our same mechanism we've done under acid-catalyzed conditions to reform from a hemiacetal back into our aldehyde. So this is why we have these two reduction schemes. Lithal, strong nucleophile, it will go through the entire cycle. It knocks off one of my groups. It exposes the ketone, the aldehyde, in the course of the reaction, which is then exposed to reduce again. It's kind of like Grignard's adding to esters. Dibal forms a stable intermediate. It hides as the acetal until you do the workup. Once you do the workup, I've done this step here, I've destroyed any other hydride that might be in the system, so there's no chance of over-reduction. I get my aldehyde out from that system. So that's the overall sort of sequence that we get through this point. Hydrolysis, really the second step right here, forming the stable intermediate, where this is step 2, this is step 1, allows us to sort of split this mechanism up and give us structurally our final outcome. Okay? Any questions? Yeah?
Why do we need the bulky alkyl groups?
It's really just a function of the reagent, dibal. What you're trying to do is you're trying to convert aluminum hydride into something where there's only one hydrogen, not too many. The bulky group just allows us to, like remember, we said that these aluminums as trivalent, they are Lewis acids. We're trying to add sterics to make the thing stable as a neutral aluminum species without coordinating to everything in sight. So it's mainly just about handling. You could do it with other double alkyl groups, so dimethyl aluminum hydride would work, but the more sort of carbon you put on it, the easier it is to handle. That's really it. So it's not so much about it has to be this group. That's just a consequence of adding enough carbon to make the thing a little bit more chilled out. So if you took this molecule and you did the reaction with dibal at minus 78 degrees, you're setting yourself up for everything else and then workup. What's the product you do here? This is a lactone. You take a lactone and you do this cleavage. First of all, what did we say about targeted groups? If I'm taking dibal and an ester, the only reason I take dibal and an ester is to make what functional group? What am I trying to do here? 2 reductions or only 1? It's only for 1 reduction. That's what I'm hoping to do. When you do 1 reduction, if you're decomposing it, step 1 is you focus on the aldehyde. That's what's happening in the system. If I'm doing a reduction in the aldehyde, that carbonyl is where the reduction is going to happen. That's my electrophilic center. That's where the hydrogen is going to be added to. So, carbons, I have the same, let's number them off, 1, 2, 3, and 4, which means I will have, I'm just going to draw it out as a 4-carbon chain for now. 1, 2, 3, and 4. Now as I do this reduction, I am clipping that bond. The bond between the carbonyl carbon and the alcohol is being fractured when you do this reduction. I'm replacing it, a carbon-oxygen bond, with a carbon-hydrogen. So I know that carbon 1 is going to have a hydrogen attached to it. That's why I did this reaction, right? That's overall that species. What else has to be at carbon 1? Aldehyde, ketone, ester, alcohol. Yeah, it's going to be your aldehyde. Carbonyl 1 is going from this higher oxidation state, this ester, down 1 to your aldehyde. Carbon 1 is your electrophilic center that's being knocked down from this high oxidation to lower oxidation state. What it also means is carbon 4 contains the alcohol we ejected. That oxygen right there is the thing that broke off from this point. So what you're doing is you're breaking this higher oxidation center down to this lower ring aldehyde. It'll be this aldehyde alcohol. Now, after workup, anything else? What might this actually do here if you had this 4-carbon system with 1 oxygen? This is what kind of a ring could you form? Yeah, this is basically setting up for I have an alcohol and this center. I could make a 5-membered ring, oxygen over here, where I've got this guy, right? This is just your open chain and your closed chain form of your acetal hemiacetal, the hemiacetal and your open chain aldehyde would be those species. So something like this might be what you actually exist here, right? Any other questions on that? Okay, last thing. So we talked about taking an amide and we can reduce it to get your amines. We've done other things with amines as well, reductive amination, whatever. But if you had to install an amine into a system, what do you guys do? What are the reactions you know to actually make primary amines? We talked about one beginning. What else do you guys have? If you had to do it by SN2, what would you use? What's that? So you want to take an R, C, triple N, and then do the reduction, right? Yep, that works. That'll get you reduction over here. Totally works. And then that way what you've done is you've got this longer carbon chain where, let's say you've got this carbon, nitrogen, you've added to this center here 2 hydrogens, right? That works. And how you might do this by SN2, maybe I installed that group from something like iodide, right? Where I added Cn minus to that center. I guess the only challenge with that is you're extending the carbon chain by 1 part. If this is where I really, really, really want this, oops. I want to take that carbon attached here. So I want not this kind of skip carbon like this where I'm adding a carbon and a nitrogen. What if I'm really, really, really picky and I only want to add a nitrogen to a system? If you did this by SN2, what's your reagent? Yeah.
NaNH2?
Sodium amide. Yeah, okay, again, wild man. This is terrible. Oh my God. Again, sodium amide, again, you can do it. That's one of those things where you can see the color of electrons, right? Like this is a very, very dangerous reagent. This is where you can go to infomercial point. How would you like a room temperature, works in water way to install nitrogens? This is what the Gabriel synthesis is for, right? If you want to surgically install a nitrogen, what they came up with was this strategy. Now, why it exists here is because it's really related. Part of this thing is related to our acyl substitutions. And we're taking advantage of a kind of reagent we've seen before, a functional group, that you might remember. If I had, right here, look at this. If this center here, just focus on that. If that was an oxygen in between the two, what do we call that functional group? 2 carbonyls, oxygen in the middle, that is called an anhydride. This is it's right there. It is an imide. It's not an imine. It's not an amide. It's an imide. It's a fusion between those two. Fun, right? So we'll go through the mechanism then on Friday. I'll see you guys then. Okay, so for our problems today, we're going to do the lithium aluminum hydride reduction of this lactone. Now, just for identifying components, remember this ester here is the group we're going to be targeting. Lithium aluminum hydride will reduce this ester all the way down to a primary alcohol. Now, just to decompose it, remember the electrophilic center is this center here, which means we're going to fragment that bond. The group that's going to become the primary alcohol because of reduction is here, meaning we're adding hydrogens to this red carbonyl. The other fragment, this piece over here, that's the alcohol that will be ejected from it as we fragment the ester. So that's just some of the decomposition we want to focus on. If you just want to draw the product, again, just targeting it, we're going to reduce this center. It means we have carbons 1, 2, 3, 4 across this point. So I'm just going to redraw that carbon skeleton first. Carbon 4, starting at that end, has the other oxygen attached. That will now be an alcohol. Carbon 4 also has a methyl group. That's this fragment over here. And then also carbon 1 on the other side, that's the center that will still contain the oxygen. This is the carbonyl, now reduced, and we've added 2 hydrogens to it. Those come from the lithium aluminum hydride. By the mechanism, that's just passing through what we showed you in this previous ones. We're taking that ester group, we're adding our lithium aluminum hydride, that's giving us our tetrahedral intermediate, which then collapses, and that's where that bond fragmentation happens. So this is just the localized version of what we're showing you over here. So one thing I just wanted to pull attention to was discussing mechanistically why we end up with this specific product here. This is the reduction where the group we're losing is actually the oxygen. We're not fragmenting this carbon-nitrogen bond. The analogy I gave you was think of it like we're fragmenting across this sigma bond here. So just to show you mechanistically what that looks like, let's say we have our primary amide. Now it works for any amide, not just the primary amides. And let's say we have lithium aluminum hydride. Once again, this is our strong nucleophile, H minus, and give us our R group here. The mechanism would look similar opening like we've done. Let's say it's a nucleophilic addition to this carbonyl. That's going to form our O minus, our N, let's keep the color coding constant. This is NH2, our R group. We've added our hydrogen, and we now have our aluminum trivalent complex like this. So now we have 2 possible paths that you might pursue. If we tried to use like we did with the ester, let's say we're going to try to bring down this oxyanion to reform our carbonyl, and that would require us to eject this nitrogen. Now under these conditions, that's a little bit of a problem, right? If I tried to just do this addition as it is, then I'm going to be kicking off NH2 minus as a group. So that's not allowed. We're not going to do something like that because that's a very bad leaving group as it stands. Okay, so that's one option. Maybe we could look at this a little different and say, well, you know what? We have a Lewis acidic system right here. Maybe what we could do is coordinate this onto here. Now we have lone pairs both on the nitrogen, but right now the lone pairs on this oxygen are more available. It's already an oxyanion. That coordination to aluminum gives also a stronger aluminum to oxygen bond rather than aluminum to nitrogen. The aluminum oxygen bond is a much tighter, much stronger bond. So that kind of follows like what we saw with the dibal. We're going to get a coordinate complex like this, where we now have our hydrogen, our NH2 attached, and we've got the aluminum now back to our strong nucleophile, like this. Actually, let me draw that just a little different. Like this. Now, there's a couple ways I've seen this drawn. Let me show you both options. Now, remember, when we've done this, this is now negatively charged, and there's kind of two ways to look at this species. First, this is now primed to act as a hydride donor, right? These H minuses are going to be nucleophilic again, and we can use them for potentially reduction. However, this center does not have another pi bond in it. We can't do a direct reduction the same way we do with dival. So we could potentially use it for something else. I'll show you that in a second. The other thing we've done here is by coordinating on this oxygen like this. Here, as this O minus, it's not going to act like a leaving group, but by coordinating like this, what we've done effectively is it's almost like protonating that oxygen. We made it into a slightly better leaving group than O minus already is here because we've coordinated this aluminum. So I've seen one option looks like this, where you take the lone pair, you bring it down, and you kick out that group. So but what we're saying here is the coordination of this oxygen aluminum bond makes it into a better leaving group. The nitrogen lone pair here can act as your nucleophile, and we're basically providing this to do an ejection. Now, I don't love this mechanism, and I'll show you why here in a second. If you follow out the arrows we've just drawn, you can make a structure like this. We've got our hydrogen. The nitrogen is now going to be an imine, which is good. Now we're back to something we can continue to reduce. But look at the group you've kicked off. Here we've got the aluminum still as a tetracoordinate system. So you still have these three hydrogens left. You still have this oxygen, which is negatively charged here and negatively charged there. So it's a -2 complex. Now again, not the worst thing in the world. Something like aluminum, you can think of it kind of like H2SO4. It's kind of like a polyvalent acid, so maybe a -2 species is possible. We do have a lot of lithium in the solution, so we have ions that may charge balance it. But this is something you'll see on sort of master organic chemistry. I've seen it in some other textbooks explained this way too, as this is generically what's happening. Really what they're trying to capture in this moment is to say, once we get to a complex like this, fragmenting this bond is bad, so we're not going to do this move. Instead, we know we want to get rid of this oxygen. That's the outcome of this reaction. So we're going to first coordinate the oxygen to aluminum to stabilize that part first. And now we're using the lone pair to eject it, giving us back this carbon-nitrogen pi bond. Let me show you a mechanism that's a little bit more general that I think actually is a better representation of how you can think about it. And it kind of follows the rules we started discussed here in class today. Instead of just immediately doing this, ejection, the molecule we have here right now, this is effectively a hydride source, H-. And because of that, the hydride could do other things like picking off this hydrogen on this nitrogen. So just let me show you what that does. What we're doing here with this kind of move is we are coordinating the aluminum. We still have this hydrogen. The nitrogen now is negatively charged. What we've done is picked off that proton. We've made one equivalent of hydrogen gas by doing this, and we've got now aluminum as the tricoordinate species. So we've gone back to aluminum's a neutral species like this. This is now going to allow us to do that move that we were discussing before. It closes off that center, and we get, let me just move this up here, we get a molecule that is still our imine type system, right? This, NH, and one equivalent over here. So it's now the neutral imine system, and we fragmented or lost this now aluminum H2O minus type species. So at least it's a -1 complex, not a -2 complex. Once we've got this one, any other lithium aluminum hydride in the solution can reduce it the same way that our aldehyde in the previous mechanisms could have been reduced. So it's just a second equivalent of hydride adding to this one to give us a second addition, where once again we're going to come down to a fully reduced center at that point. That gives us our primary amine like we're showing over here. Now, either mechanisms are acceptable if you want to sort of draw them off. The key thing we have to focus on for this mechanism is the first addition of the hydride to our amide gives us a tetrahedral intermediate. That's definitely true. That's the first addition of this hydrogen. This tetrahedral intermediate, looking right at the center, is kind of like an acetal. It's kind of like one of the intermediates you've seen for imine formation. So what we have to do is coordinate this oxygen to give your aluminum. We're going to use that as our way to eject this in the same way we'd use a proton to eject this oxygen. That forms an imine, which then is reduced one more time. And there's a preference to lose the carbon-oxygen bond rather than the carbon-nitrogen bond, mainly because, first of all, oxygen-aluminum is a very tight bond. Second, if we tried to do the reciprocal, like we're just doing this, we'd try to be ejecting a nitrogen minus as a leaving group, which is definitely not favored.